some balls of some color. So only one color at each vertex. And then at each step, what you do is you choose uniformly a ball. Okay, so you might choose uniformly one ball. One ball. And then this ball sends a copy of itself down each edge to each of its neighbors. If the ball's in the neighbor of the same color, that ball stays there, adds one. If they're a different color, then it annihilates one of the balls. So the number of balls decreases by one. Okay? So, theorem of Daniel Alberg, Simon Griffiths, Svante Janssen, and myself, fairly recent, is that on every finite graph, if there are with any initial configuration with two colors only, one of the colors wins. So for all G, two colors implies, in Joel's language, total domination. Thank you. Yeah. Thank you, Simon. Question. So the first natural question you all think I'm going to say is this true for three or more colors? The answer is no. Here is a simple graph on which the answer is no. Put lots of red here, lots of green here, and lots of blue here, and nothing here. So what happens in this graph, when you pick a green ball, it gives these things reinforce each other. These things reinforce each other. These things reinforce each other. They also send 10 balls to the middle, but if, say, red is here, he's being attacked by both blue and green, and only reinforced by red. So he's likely to go back to 0. So this you can prove without too much difficulty. This has some non-zero chance of all three colors surviving. Okay, question. What about three colors on a cycle? I'll put CN. Okay, so the natural thing to suspect is that one of the colors wins, but this seems harder than one might think. So I think this is a nice problem, which maybe someone could solve, or some group can solve this week. Questions?
What about 10 colors on the cycle?
Right. So I mean, so the thing about three. So if you think about, say, why didn't I say a path? Because suppose you have 10 colors on a path, you could just rename the colors, make them alternate colors, apply this theorem, one of the colors dies, and just repeat. So on the path, it follows from the theorem, but on the cycle, then because sort of three colors you can't turn them into two colors. So I guess with 100 colors, you could turn them into three colors by going, or in 100 colors you can turn into two colors, but then one of them dies. Yeah. So if you do three, then I guess you can do anything. Follow immediately? I mean, I think it follows, yeah. You can do anything. Yeah, so chromatic number or whatever. You want to do chromatic number on, yeah. More questions? Yeah? Right, so let me do it on give you a small example. So this is like red, red, green, blue, 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 green, or something. So how many balls are there? Are 4, 5, 6, 7, 8 balls. So I pick each one with equal probability 1/8. So maybe I pick this one. So he sends a blue here, so you get an extra blue here. He sends a blue here, you get an extra blue here. And then these two annihilate each other. So then you're with nothing here. That's the next step.
And the blue disappears from
No, sorry, he sends a copy of himself. Thank you, yeah. So it builds up. Yeah. And then you pick another one, so this red one, he sends a red one here, and he annihilates the green. Now we're down to 2 colors, and so now someone wins. Shall I do another step? And then It's clear? Okay. More questions? Okay. Who's next? That's my question. Don't be shy.
Take one. But actually, this is not my problem. In fact, it's Rob Morris's and Annika, I don't know her last name, Heka at Oxford, and Bela Bolabash, and maybe other people as well. So the question is about the, you take the random graph, say p equals 1/2, and you look at the chromatic number, and so there are upper bounds on the concentration of the chromatic number, but how about a lower bound on the concentration of the chromatic number? And I believe, Bela, you asked it for a finite number, and even that's not known. What? Over 30 years ago, yes, right. So even that's not known, but that remains open. And Rob has some very good heuristics that the concentration, the width of the concentration should actually be a power of n, which kind of varies between n to the 1/4 and n to the 1/2. But again, it's heuristics. So even Bela's question from 30 years ago remains open, that it might be concentrated in only a constant number, but on the other hand, maybe the concentration is only in a power of n, where in fact that power of n might get quite close to n to the 1/2, where on the other side it's known that the concentration is in root n. So that's open. Yeah. Yeah. Exactly. Yeah. Thank you. Next, lunch.